Hi, welcome to the second session on countable and uncountable sets. So, in the last lecture, we already touched upon Cantor's ingenious idea saying that two sets have the same number of elements, that is within quotation marks, if and only if there is a bijection between x and y. Okay, so let us go through it carefully and try to do some things. So again, let me say these are all the my channel, and any kind of email about these videos, please send it to here, not to my personal email ID. And if you want to download the list of videos, you have to go here. And the importance of that list is that topic wise the videos are arranged with URLs are also given and brief descriptions are also given. It is also in the order of preference, in which way you should, if you want to learn a subject, what is the order which you should watch the videos. All these things are given because YouTube does not have a very nice way of displaying these things, so please go through it. Okay, so let us start with the first thing. I have two sets x and y. I say x and y have the same number of elements. If there is a bijection, f from x to y. Okay, but the correct word is x and y have the same cardinality. The modern way is the same cardinality. C-A-R-D-I-N-A-L-I-T-Y, cardinality. Okay, so we will just look at one particular example why when Cantor proposed this kind of idea, okay, his contemporary mathematicians who were living around that, most of them were shocked. Okay, they didn't want to accept this definition at first. Whenever there is a radically different ideas, there is always a resistance in the community. Okay, that's a very common throughout history. That's what happened here also. So let us look at my x equal to, let us say, all natural numbers, y equal to all even numbers, set of even numbers. Okay, then I have a bijection from x to y, namely f of n equal to 2n. This is a bijection. Okay, therefore you want to say x and y have the same number of elements. If you use that word, now you see that you think that y is exactly half the size of x, so how can they have the same number of elements? You follow what I am saying? So these are the troubles which mathematicians, great mathematicians in fact, of that age had problem. So you simply say they have the same cardinality. In fact, this can be much worse. Okay, for example, suppose fix a prime p. Okay, then let us look at p power n as n varies over n. Okay, and this is a set which I call as z. Okay, let me call it as b, and let's look at set of natural numbers n to b. There is a bijection, f of n equal to p to the power n. This is a bijection, right? Again, you can see this is very shocking, because if p, there are infinitely many primes, so if I take a p which is very large prime, okay, then p power n will be very sparse, something like, let's say I'm on, okay, millionth prime, then millionth prime squared, millionth prime cubed, they will be far away, right? But I want to say they have the same cardinality. Yeah, a much worse situation, all of you know the set of primes, let us call it, okay, p is the set of prime, this is infinite. Okay, we have not, okay, I don't want to define infinite set, we will do it later, but all of you know what it means infinite. Okay, so now let us look at for each n, so let me call it k. For each k you define pk power n as n varies over natural numbers. Okay, for each. Now you can see ak and ar are disjoint if k and r are different. Okay, the kth prime and rth prime if are different, then these are empty. Okay, therefore for each k I have infinitely many things, so I have a disjoint union of ak, and k varies over n, all natural numbers, right? Or what does it mean? Try to understand. Ak simply means take the kth prime and take it all its powers, that's all it means. Okay, this is disjoint, and this is a proper subset of natural numbers, you understand, and each one of them is in bijective correspondence with n, and there are infinitely many, and this is a proper set. For example, if I have something like 2, 3, etc., 5, right, this number 2 times 3 times 5 squared will not be in any one of them, you understand that, because a2 will have only, or sorry, a1, that's the first prime, that will have only 2 squared, and a2, this is 3, that will be 3 squared, and a3 will be 5 squared, 5 cubed, but this number will not be there. So it's a very proper subset of natural number, you understand, but each one of this is bijective correspondence with n. You can see how difficult for people to imagine this. Okay, pause, review, proceed. To proceed further, okay, let us look at this example a little more carefully. Right, now I want to say again, okay, n and the set of integers have the same cardinality, that is, they have the same number of elements. Okay, I'm just for make us understand, I'm saying same number of elements. Now the modern way to say is they have the same cardinality, right, because I want to set up a bijection. How do I do that? Let us look at. So I write 0, 2, 3, 4, 5, 6, 7, minus 1, minus 2, minus 3, minus 4, and so on, minus 5, etc. Right? I have now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. This is my z, this is my natural numbers. I want to set up a bijection. Okay, let us do it by hand and then write down a formula. Now 0 goes to 1. Maybe I should use a different color. Okay, let us say 0 goes to 1. Okay, and where does this fellow go? 1 will go to 2. Okay, then I come to minus 1. I will make minus 1 go to 3. Okay, now where will 2 go? 2 will go to 4. Okay, where do you think minus 2 should go? Minus 2 should go to 5. Right, and where will 3 go? 3 will go to 6. Don't get bored, let us do it. And where do you think minus 3 will go? Minus 3 will go to 7. Now do you see a pattern? What is the pattern? Pattern is f of f from z to n I am defining. How do I define? F of 0 is 1. And f of n, if n is a natural number, where does it go to? Look at that. It goes to 2n. 1 goes to 2, 2 goes to 4, 3 goes to 6, 4 will go to 8 because minus 3 into 7. And where will f of minus n will go? Okay, where again n is n, therefore this is negative. So where will it go? Just so that minus 1 into 3, minus 2 into 5, minus 3 into 7, therefore it went to 1 plus 2 times mod n. Do you understand that? Okay. So we claim f is 1, 1. Okay. Now notice that f of 0 is different from f of n for any n in z and n not equal to 0. Why? Because f of 0 is 1, but f of n are all greater than or equal to 2. Right? That's clear. Now, if an m and n both belong to n, then what is the for f of n will be 2m and f of n will be 2n, and if they are equal, that means m equal to n. Okay, the f of m equal to f of n if and only if m equal to n. And similarly, if m and n are n, but let us look at f of minus m. If I say f of that's equal to f of minus n, that means 2 of mod m plus 1 equal to 2 of mod n plus, sorry, let me write, sorry, 2 of m plus 1 equal to 2 of n plus 1. Right? So I should write 1 plus 2n. Okay? Are you following? Because it's a minus n, because n is already positive, so I should write that. That's what I'm saying. Yeah? So this implies again m equal to n. And if m is in n and okay, I am taking minus n, if I say f of m equal to f of minus n, can it happen? Because this will be 2m, this will be 2n plus 1, this is even, this is odd, therefore they are never equal. So I have computed f is 1 1. Okay, pause, review, proceed. Then I have to say f is onto, right? So you give me any n, in n I have to find a pre-image, right? That is clear. If n equal to 1, then f of 0 is 1. Okay, and if n equal to 2k, then f of k equal to 2k. And if n equal to 2k plus 1, then f of minus k is n. Right? Is that clear? That's how we define. So f is 1 1 on 2 is a bijection. Therefore, okay, these two have the same cardinality. You see that? But how will I write z? Z as n union minus n. What is minus n? Minus n is all union singleton 0. Right? So z seems to have twice as number of elements as in n and plus one extra element. but according to Cantor, they have the same number of elements. That is, they have the same cardinality. Do you follow that? Okay. The easier thing is, let us say z plus is, okay, all non-negative integers and n. They are bijection. Okay, because how will I do? F of z plus 2n, I will simply say f of n equal to n plus 1. That's it. Okay, this is a bijection. It's very easy to check. Do you understand these things? Did I share? Yes, good. I was not sure about that. Okay, is it running? Yes. Okay, is that clear? So we have done that. Now next thing, I want to say something much worse. Let us look at z plus. Okay, let me write. I want to say n cross n and n have the same number of elements. Have the same cardinality. You see that is much worse. Right? Even the product is ordered pairs of m and n. Okay, and I have bijection with this. So how will I do that? The trick is something to do with prime factorization. See, if I give me any integer n, I can write it always 2 power r into s, okay, where r is greater than or equal to 0 and s is odd. You understand that? You write down the prime factorization, something like 2 power r into some p2 power, okay, something m2 and p3 power m3 and so on. All the prime factorization, these are all odd primes, right? So this will be odd. Are you following? I can always write like that, right? So I want to make use of that. So what I want to do is, if you give me m and n, I want to map it to 2 to the power m into 2n plus 1. Okay, this is a basic idea, basic naive idea. Okay, it may or may not work, but we are going to see that. Now remember, m and n are natural numbers. If that be the case, this will be at least 2 and this will at least be 3. So this will be always greater than or equal to 6. Right? So I will not be able to get on 2. Are you following? Right? I will not even be able to get 1. I will not be able to get 2, etc. So the one thing may be, suppose if I allow m and n to be in z plus, then I will get this. So z plus, then I will have 2 to the power m. So if I take m equal to 0, right, then I will have an odd number. And if I take only even number 2, I can take m equal to 1 and n equal to 0. Are you following me? F of 1 0 will be 2, right, and f of 0 1 will be, what is 1 0? This is 2 and this is 0 1, and f of 0 1, this is 0 and this will be 3. Okay, but how do I get 1? And I get f of 0 and 0, I will get 1, because m to the power 0 will be 0, this will be 1. You follow? Yeah. So now, therefore, what I want to do is, I want to look at z plus cross z plus to z plus. Then I want to get 0. Okay. Now you follow what I mean? This n and n I changed to n z plus and z plus. So I got 1. Okay. But what I want to do is, I don't want z plus cross z plus to n, but I want to show it z plus. That means I want to get 0 now. I got 1, but I have to get 0. How do you think I will get 0? So you simply modify that, f of mn equal to 2 to the power n 2n plus 1 minus 1. Okay. I can simply define this function, but I will try to explain how I arrived at it. Okay. Now, is this function 1 1? Yeah. Suppose f of mn equal to f of rs. What does that mean? 2 to the power m 2n plus 1 minus 1 equal to 2 to the power r 2s plus 1 minus 1. Therefore these are equal, right? Now this is a prime factorization of two numbers, therefore r must be equal to m must be equal to r, and therefore 2n plus 1 must be equal to 2s plus 1. That implies n equal to s. Okay, pause, review, proceed. Therefore f is 1 1. Okay, so is f on 2. Okay, what does that mean? That is, you are going to give me, let us say, a k in z plus, then I have to find m and n in z plus cross z plus, so that f of mn equal to k. But what is f of mn? 2 to the power m plus 2n plus 1 minus 1 equal to k. That is 2 to the power m 2n plus 1 equal to k plus 1. Now remember, k plus 1, k is in z plus, therefore k plus 1. First notice that if k is 0, we already found f of 0 0 is 0, right? Did we find it? Somewhere we do. Yeah, f of 0 0 is 0 1. Sorry. Yeah. What is f of 0 0? F of 0 0 will be, this is 0, therefore it's 1, and this is 0 1, 1 into 1 1 minus 1, that is 0. Okay, therefore we got it, right? So let me assume k is greater than k, and suppose k equal to 1, then also I know that if k equal to 1, this is equal to, if k is 1, this is equal to 2. Okay, then I want 2 to the power m 2n plus 1, therefore I can take n to be 0 and m equal to 1. Yeah, Do all of you follow that? Therefore I can assume my k is greater than or equal to 3. Okay. Now this k, I can write it as some 2 power r into some l, where l is odd. You understand? Therefore I want, sorry, not k, k plus 1. Therefore I want k plus 1. Okay. K plus 1 to be 2 to the power r into l. I write it this way. Then what do I want? I want 2 to the power m 2n plus 1 equal to 2 to the power r into l, and l is also odd. Therefore my m must be equal to r, right? And 2n plus 1 equal to l. Therefore 2n equal to l minus 1. Therefore n equal to l minus 1 by 2. Now remember l is greater than or equal to 3. Therefore l minus 1 will be greater than or equal to 2. First l is odd. Therefore this will be even. Therefore I can divide by 2. Therefore this belongs to n. Are you following? So I found it r. So then it is very easy to check f of r. F of mn, where m equal to r and n equal to l minus 1 by 2. What are r and s? That is the description of k plus 1 in terms of the prime factorization 2. Is that clear to you? Therefore it is equal to k plus 1. Okay. So please check PRP. Therefore we have proved f is z plus cross z plus to z plus is a bijection, right? This is z plus again. Therefore I have a bijection because z plus is a bijection. There is a bijection, call it phi to m, and cross z plus the same bijection. Okay, this is a cross. Therefore this will be a bijection, right? If I have mn, send it to m plus 1, n plus 1. This is a bijection. Okay. Now whatever is a bijection f, okay, I can bring a bijection to n also now. So this is z plus. Now I have the same bijection here. Yeah. So if I combine, I actually get a bijection from n cross n to n. Call it G. Okay, you can write down, but let's not worry about it. Okay, we will do something else. So what are the things? So pause, review, proceed. So what are the things we found? If I adapt Cantor's definition, okay, there are a lot of shocking things. Okay, n and z has the same number of elements. Let's z plus, and n and z has the same number of elements, right? And n and any p power n in n has the same number of elements, where p is a prime, right? And z plus cross z plus 2 z plus, okay, they have the same number of elements, that is they have the same cardinality, and hence n cross n and n have the same cardinality. Okay, these are the shocking results, because z n cross n looks much bigger than n, but you are saying they have the same cardinality. These are the kind of things which really repulsed, okay, mathematicians of past. Okay, then they slowly working on that, you get used to it. Okay, this is a very good way of looking at the thing. Okay, so pause, review, proceed. Now I want to define, okay, I want some facts about finite sets before I go further. Okay, so suppose, yes, give me a set x. Okay, x is not empty. I say x is finite. Okay, let in denote the initial segment of natural numbers 1 to n. Okay, right? I say x is finite if there exists a bijection f of x to in, right? So it simply means that you are counting for each element x, you are writing, okay, or if you want a bijection in to x, if you want, you write it. Therefore the image you call it as xn. X1 will be xk, k will go to xk, f of x, f of k, you call it xk. So you can write x as x1 to xk. That is how you do that. Yeah, sorry, x1, x2, xn. Okay, are you happy? Don't worry about some trivial goofings. That's a very idea is clear, right? Now there is a natural question. Okay, it simply means I am counting the number of elements. That's all it says in x. But can it happen? There is a bijection f from, let us say, im to x, and g a bijection from im to x. Okay, where m and n are natural numbers. Okay, then the theorem says, okay, if these are all bijections, then m equal to n. What does it mean? It means that you give me a set x, you are counting, and the same set you are also counting. So you may say that it has m elements, I may say it has n elements. Okay, but the theorem says no, then m must be n. Okay, you can imagine, because if I have a very huge pile of coins, if I count, I may get some number. If you count, you may get some more number. A third person will count some other number, but all of us are convinced, okay, there is only one particular number. There is enough this number of coins. Okay, you understand? So how do I assure that? Because of this theorem. Okay, so let us accept it. Okay, then I say n is the number of elements. Number of elements of x, because now it is unique. Okay, notice that counting may be different. You may count something as the first element, second element. I may count in a different way. Okay, but the point is number of elements will be the same. Are you following me? Yeah. Okay, right. The next thing we have to see is if A is a subset of B, and suppose B is finite with n elements, okay, then A is finite, and number of elements in A will be less than or equal to n. Number of elements in B. Okay, these are the very facts. And similarly, if A and B are finite, then A union B is finite. Okay, these are the very small thing. Okay, a third thing will also be useful. Okay, from that it will follow, because if I have, suppose I have an injection f from a set A to in, it's a 1-1 map. Okay, then what do you think you can say? Then one usually denotes by mod A the number of elements. So mod A will be less than or equal to n. How do I know that? Yeah, because in, okay, see, can in, there can be if there is a bijection to in and im, then n equal to m. That's what we just now saw. Alright, therefore if in has n number of elements and A is a subset, if by injection f of A is a subset of in, right? Therefore number of elements of f of A will be less than or equal to n. But since A and fa are bijection, okay, they have the same number of elements. Okay, so all these things we will prove rigorously in some other video, or you can refer to my book, refer to foundation book. Which was given as a reference. Okay, right. With this, now I want to define countable sets. So how do I define countable sets? Okay, yeah, in finite set there is one more thing which I should say. I say if x is empty, then also I say it is finite set, and the number of elements in x is of course 0. Okay, that's a convention, right? Okay. So when I say X is a finite set, either X is empty or it's non-empty, then it has a bijection with some in for some n. Okay, there exists n in n, such that there is a bijection X to in. Okay, so when do I say it's a countable set? Suppose X is a set. Okay, I say X is countable if either X is finite, that means X could be empty, or X is a non-empty finite set, or okay, or 2, there exists a bijection f to n. So you understand this? If 2 happens, I say X is countably infinite. Okay, so when do I say a set X is infinite? If only if X is not finite. Okay, so I say X is countably infinite if there is a bijection of X to n. So any countable set intuitively should mean, okay, it is either a subset of n, finite subset of n, or it is as good as n, because there is a bijection. It's intuition. Okay, don't take it okay complete as a truth, but you should have a feeling. Okay, are you following me? Now I claim n is infinite set and it's countably infinite. There is a bijection of n to n, take it as x to n, namely identity n goes to n. Okay, therefore it's countable. Okay, n is countable. Then I want to say it is infinite. If it is finite, what does it mean? There is a bijection. If it is finite, there is a bijection of n to some in. Right? Now is a bijection. Am I right? Now let's look at n plus 1. It's n plus 2, etc. Where will they go? G of n plus 1 should be in n in. Right? So what do I have? I have lot of elements. They will have. There is why we need some kind of pigeonhole principle. What does it say? It also follows from my earlier thing. That is why one has to go through finite set. Just because you people wanted countable, I already started. Okay, if f from let us say in to im, and if n is strictly greater than m, okay, then okay there exists in j in in, so that f of I equal to f of j. That means think of them as pigeonholes, pigeon boxes, and these are the pigeons. Okay, there are n number of pigeons, where number of pigeons is strictly greater than number of holes. Then at least 2 pigeons have to sit in the same hole. They will be assigned to the same hole. Right? Therefore, if I take this, now let's look at I of n plus 1, which is already in n. Okay, therefore, when I restrict g to that, therefore I will have g from I of n plus 1 to in. This will be a 1-1 map, because restriction of any 1-1 map is again 1-1. Okay, but this says it's not 1-1. Pigeonhole principle says it's not 1-1. Are you following? Am I making myself clear? Okay, the best way is pause the video, play it again. Okay, so that now do you also understand? To make things rigorous, I have to do something about finite sets also rigorously. As I said, sometime later I may do it, or you can read it from the book. Okay, but many of the things which I am saying are intuitively clear. What did we say? We said that n is an infinite set. That is very clear to you, right? and it is countable because of this. Is that clear? Very good. Right, now what do I want to do? Right, now I want to show two things. Okay, I want to prove a theorem which will make our life easy. The following, let X be a set. The following are equivalent statement. That is, we are trying to find equivalent conditions for a set to be countable. One is X is countable. That we have a definition, right? And two, there exists a 1-1 map F from X to N, and 3, there exists an onto map G from N to X. Okay, these are all intuitively clear if you are ready to visualize that. Okay, we will go through a proof. Do you understand this? So I have N 1, 2, 3, etc., etc., and the set something, I have an onto map, right, for E. So therefore there may be many elements, you may be coming to the same point. Therefore what do I have is, in some sense, okay, it is smaller than this. Okay, if you don't want to have that kind of intuition, leave it. So suppose X is countable, I will prove 1 implies 2. Therefore, okay, suppose X is finite. Okay, if it is empty set, again we will allow empty set should be countable, because any finite set is countable. Therefore let us assume this. So when I say there is a empty set, okay, if you want, say non-empty set, because empty set is finite and hence is countable, so let us forget about it. Because if I have an empty set as X, then I have to think of a map, then you will get into logical confusion. So let's not worry about. Let X be a non-empty set, then the following are equivalent. X is a countable set, a non-empty countable set obviously, and there is a 1-1 map of X into N, and there is an onto map G from N to X. Okay, so suppose X is finite, therefore X is non-empty. Therefore what does it mean? There exists a map F which is from X to N and 1-1 map, right? Sorry, a 1-1 map into In. So there exists, if X is finite, there exists N natural number and a bijection F from X to In, right? Now let's look at In, the inclusion map into N. This is the inclusion, that is restriction of identity, that is K goes to K itself, right? Now the composite map is a map from X to N. This is also 1-1, right? If you want to call it I, this map is F composite I. F goes from X to In and In goes to N by composite inclusion map. Okay, therefore I composite F of X is nothing other than Fx, right? Fx goes to itself. Okay, this is a 1-1 map, right? Therefore this is a 1-1 map of X into N. Therefore 1 implies 2 is clear. Now I want to prove 2 implies 3. What is 2? 2 says there is a 1-1 map of X into N. What do I have to prove? Okay, I want to prove there is a G from N to X which is onto. Right. So how do we think I will do? See, this is a 1-1 map, therefore you can see there may not be, okay, the image of Fx may not be all of N, because 1-1 map, it's not onto, right? You understand? Therefore what I have to do is very simple. Again, it is highly intuitive. If you look at the picture which I drew here, that's what I am going to do now. Okay, I have X and 1, 2, 3, etc. Okay, I have some injective map. Let's not worry about. Okay, I will draw either, but it can go here, this can go here, etc. But let's not worry about. Okay, I have this. Then this element may not even be there, so I want to map it. So it's a 1-1 map. Therefore, if I take N, okay, there are two cases. I can write N as, okay, F of X union n minus f of x, the complement of that. You understand that? Right? Now notice that f is a 1-1 map, therefore f to fx, this is a bijection. Yes? Therefore, if it start with an n in fx, okay, there is a unique n because f is 1-1, okay, in x, such that f of n equal to x. Therefore, define g of x equal to n. Yeah, whatever is here, if it is there, look for the unique element, and this is the map, it goes this way now. Yeah. Now suppose n is not in fx, what do I do? Then you fix some element, fix some p in x, okay, then define g of, I want from, say, g of n to be, sorry, I'm sorry, I think I'm trying to rush. If n is in fx, there is a unique x in x such that fx equal to n, therefore define g of n equal to x. Is it okay? So I have an n, okay, if it's n in fx, then x is a unique x such that it gets mapped to this n, therefore I go in the reverse direction now, this n goes to x, okay, right. And suppose n is not in fx, then I define g of n to be some p. P is some element, I don't care. Fix p, fixed element of x. Okay. Now what do I want to claim? And g from n to x is on to. But that is clear. Why? Give me any x in capital X. Okay. Then f is from x to n. Therefore fx equal to n. Therefore g of, okay, g of n equal to x. Right. So for each x here, I have at least one n so that g of n equal to x. Therefore this is on to. So what do you think I have proved? Okay. If f is from x to n is 1-1, implies there is a g from n to x on to. That is 2 implies 3. Okay. Now I want to prove 3 implies 1. What is 3? There is a g from n to x which is on to. Okay. What do I want to do? I want to prove then x is countable. Okay. How do I do that? Right. Now since it's on to, let us look at the set ax for each x in x, ax equal to set of all n in capital N such that g of n equal to x, and ax is non-empty because it's on to, right? Therefore there exists at least one n such that g of x n equal to x, therefore it's on to. Now therefore ax is a non-empty subset of natural number, therefore by well ordering principle there exists an nx such that nx is the least element of ax, right? Therefore let me define a map f from x to n such that f of x equal to nx. Right? Have you understood? Okay. I claim this map is 1-1. Why it's 1-1? Suppose f of x equal to nx, which is also equal to f of y, that is nx equal to ny. Right? Now what does that mean? This means g of nx equal to x as well as g of nx, because nx is same as ny, g of nx is equal to y. Therefore x equal to y. You understand that? but g is a function. Therefore g of nx is well defined. Okay, are you following me? Suppose fx equal to fy. Okay, then I have to prove x equal to y. Okay, right. Now fx equal to nx means what? G of nx must be x. Go back to the definition. There is an nx in gx ax, which is the least element. When nx belong to that, what does it mean? G of nx is equal to x. You follow that? Therefore g of nx is x. For the same reason, g of ny is also equal to y. Yeah, but you said nx equal to ny, therefore g of nx equal to g of ny. That means x equal to y, because g is a function. For each element it has a unique image, right? Therefore fx equal to fy implies x equal to y. Therefore f is 1 1. Right? Now what are the possibilities? Either f is on 2. In that case f is a bijection from n to x, bijection. Okay, therefore it's countable. Okay, or f is not on 2. Yeah, okay, if it's not on 2, what does it mean? Yeah, this is all I have to understand. So if f is not on 2, I claim that x is finite. That is, I have to show there is a bijection. How will I do that? Okay, let us think about. So let us slightly modify this argument. Okay, so now what are the possibilities? Let us look at the set which is I have defined, right? So I have a map from g from n to x, which is on 2. Then I define a map f from x to n, which is 1 1. Right? Okay. Now what are the possibilities? Let us look at this set nx, this collection as x varies over capital X, which is f of x. So this is a subset of n. Either this is finite set or it is an infinite set. Right? Yeah. So if it's a finite set, what do I have? I have a bijection. So if x is a finite set, right? Therefore, what do I have? I have some, let us call it, I have to have a better notation. Let me think about. So let us continue. So we have a g, okay, which is from n to x on 2. We define f from x to n. So what did you do? For each x in x, we looked at ax, set of all n in n, so that g of n equal to x, and we let n equal to the least element of ax. Okay, so we define f from n to x to be f of, okay, sorry, we want to define f from x to n. Okay, so that f of x equal to nx. So we showed f is 1 1. Okay, now what we want to show? We want to show x is countable. So if x is countable, what is our definition? Either I have to show x is finite or x there is a bijection of n with x, right? So I have to prove that. So how will I do that? Let's look at the set fx. This is a subset of n. Okay, this is non-empty set, right? Okay, now so there are two things. Okay, if either fx is finite or fx is infinite. What is mean by it's infinite? It's not finite. Okay, if fx is finite, it's a subset of natural numbers, right? Therefore I can write fx in this case, fx equal to, I can write as n1 less than n2. It's not necessary, but I can do that, right? Then I have a bijection, namely a bijection of x into some ik, where phi of x equal to k if what happens, my nk, right? I have done that, right? This nk equal to some nx, alright? Are you following? You start with an x, there is an nx, that nx appears as n1 to n2 nk, right? So I am putting that. Okay, then phi is obviously 1 1 and on 2. Is that clear? Because this is nothing other than your nx. As x here is your capital X. Okay, therefore when I say nx, it is some nj here. So it's a k, that let me say nj if nx equal to nj. So is phi 1 1? Yes. Why? Because if phi of x equal to phi of y, that means, okay, so I call this as I, this is j, but then this means this is ni and this is nj, right? They are equal. That means they are, but I have written them n1 less than n2 less than nk. Therefore I is not equal to j, then ni is not equal to ng. Are you following? Therefore phi is 1 1. Of course by very constructions on 2, because you start with any element nj, then nj is going to be nx for some x. Therefore, okay, my phi of x will be particular j. Okay, are you following? Okay, so phi is 1 1 and on 2. Therefore phi is a bijection of x into ik. Therefore x is finite. Okay, pause, review, proceed. Let me just check whether I turned on the recording. Yes. Okay, and suppose fx is infinite, right? Again I can use well ordering principle. Okay, so I can write fx as a set n1 less than n2 less than nk less than nk plus 1, etc. Right? So now can you think of a map psi from x to n? Take any x and my nx has to be here, right? Because what is fx? Fx is nx. As x here is capital, therefore nx has to be there. Okay, so my nx has to be nk for some k. So map x to k. As earlier, this psi is a bijection. Okay, so pause, review, proceed. So what is that we have shown? We have shown that if the following are equivalent, either x is countable. So if I want to check if is countable, if and only if there exists a 1 1 map of x into n, and that is if only if there is an onto map of n to x. Is it okay? So whichever is convenient, we can make use of that. So as a corollary, let us do that. Suppose I have two sets A and B. Okay, sorry, A and B, two sets. Okay, now suppose there is a map here, F from A to B, okay, which is 1 1, and B is countable. Then what can you conclude about A? A is countable, because since B is countable, there exists a G which is a 1 1 map, right, by our characterization. Therefore the composite, okay, G composite F will be a 1 1 map of A into n. Therefore A is countable. Okay, and suppose Now I have a map G from A to B which is onto. What should be the hypothesis now? I want to say something is countable, then the other is countable. Which should you think I should say that? Assume A is countable, then B is countable. Okay, why? That is again clear. Since A is countable, there is a map from N to A, let us call it Xi, which is onto, and A to B, this map G onto, this onto, this onto. Therefore, the composite, okay, G composite Xi, this is an onto map of N onto B, therefore B is countable. Okay, does it remind you of something? See, you would have seen if I have two series of positive terms, okay, then if this is convergent, then that implies this is convergent. Okay, and if this is divergent, this implies this is divergent. Something similar, you see that? Okay, not exactly the same, but you see, this is how one tries to understand mathematics. You see, there is a beauty, something very similar. Okay, right. The next thing, suppose A is a subset of B. If I say something is countable, I want to say something, the next one is countable. What should be our assumption now? Yeah, suppose B is countable, then A is countable. Why? Since A is countable, there is an inclusion map as a subset, that restriction or identity map of B to A. So that is A going to A, right? And since B is countable, there is a 1-1 map F into N. Therefore, the composite is 1-1 map of A into N. Therefore, A is countable. Okay. So pause, review, proceed. Right? Okay. Now remember, we had already proved Z plus cross Z plus to Z plus, there is a bijection. Okay, and we know this is countable. Therefore, this is countable. Do you follow that? Because this is a bijection, this is okay, this is a bijection, but this I have a bijection with N, this we had already seen, right? And there is a bijection, therefore composite will be a bijection. Therefore, in particular, it's our 1-1 map of Z plus cross Z plus to N. Are you following? Therefore, this is a 1-1 map, this is a 1-1 map. Okay, this is do you remember? This is going to N going to mute N plus 1. This is some AB going to 2 power A into 2B plus 1 minus 1. That was the map. Okay, so composite of 1-1 map, therefore this is countable, and it's countably infinite. Why? Because let's look at something like 1 cross N as N varies over Z plus. Okay, right? Now this collection is already a subset of Z plus cross Z plus, and this is, there is a bijection of this with N. Okay, or Z plus if you want, let me write N. Okay, there is a bijection, and this is countably infinite, therefore this is countably infinite, and this is countably infinite. This is just for fun. Now I want to say if A and B are countable, A union B is countable. Okay, this will actually come very easy, but just for fun, let's do that. See, if it's finite, there is nothing to prove. Okay, if one is finite, one is countable, right? So how will I get A union B is countable? I want to prove A union B is countable, right? If both are finite, then we know finite. Okay, union of finite sets is finite. That's one result which I use. Therefore, assume one is okay. Suppose A is finite and B is infinite. Okay, how will I prove that? Nothing. Okay, if B is countably infinite, you see that there is this bijection. right? Yeah, and what do I do here? I want, what do I want? I want just an one map. Yeah, so can I get something? Remember, A union B, okay, A and B may have non-empty intersection, right? You follow that? So we will think of a slightly more general result. I will prove that. Okay, just think about, I can prove it here, but I just thought of a different way. Suppose I a countable set, right? Okay, and suppose for each I in I have given A, which is a countable set, right? Now let's look at A equal to union A. This is set of all elements x in the, okay, some universal set, some x. Let us assume these are all countable subsets of x, so that x there is I in I, so that x belong to A, right? So I want to say this. I want to know whether this is countable, right? So how will I do that? Since I is countable, you see that there is this. Let us see whether I want an on1 map or on2 map. We will think about this is all I have to do. Okay, now let us do that. Z cross Z I want. Okay, so I will think of a on1 map. Yeah, right. So this is countable. Therefore, there exists a countable thing for F from I to N. This is a on1 map. Because I is countable, it exists, and for each I gi there exists a to n, one map. Okay, right? Can I also assume this is z plus? Yeah, because if I have an n1 map, then I have the map n to z plus, namely n going to n minus 1. So I compose it, so I have a 1 map. Do you follow that? Yeah. So now let us start with any x in union I in I. Okay, I want to map into z z plus cross z plus. A 1 map is what I want to do. So I know this is already countable, right? And therefore, if I have a 1 map, this just now we saw, okay, this will be automatically countable. Otherwise, you just make it 10. Okay, this is a 1 map. This will be 1 map, right? So how will I do that? You start with any x. That means there is an I in I, and so that x belong to A, right? Yeah. So what do you think I can do? This I can map it to f of I. That will be in z plus, right? Now x is in A, therefore I can map it to GA of x. Are you following? So I will think of a map phi of x equal to f of I and GA of x if x belong to A. Okay, right. But is this map well defined? Because if x belong to union A, and x may belong to two things, AJ as well as A, right? Therefore this map is not well defined, because I will have f of I or f of j, and after that j of x. So this map phi is not even defined properly. You understand that? Yes. So what do I do? So you see that we ran into a problem. Alright. So what do you think you will do? See, this method does not seem to work. So an obvious thing is try the other one. What is countability? There are three second condition which means on to, right? Maybe you can try that. See, this is how you learn mathematics, right? Okay, if I have prepared, I will know that is the correct one, so I will start with that and prove. So you got a proof, yeah, assuming that works. You follow that? Anyway, let's go back. Let me just show. Okay, so okay, we abandon this. Okay, instead, since there exists a map n into I which is onto, and there is for each I there is a map gi from n into I which is onto, right? So from these two things I want to cook up a map phi from n cross n to union A which is onto. Yeah, so how will I do that? So you start with an m and n, okay, then see, then I have this n, right? Therefore, yeah, this n I have f of n, f of m, that is in I, therefore call this I, right? Now phi of n, I will use this I to define GA of n. Are you following? I have m and n, okay, okay, m under f corresponds to some I in I, right? Now I have an n. Now I use this I under gi, it corresponds to some element in A, right? Therefore my element is going to be gi of n. If you want, I can make it look little complicated, f of m and n. How do you like this? Okay, this is phi of mn. Huh? Please understand. So what do I have? I have m and n in n cross n. Okay, under f my m goes to an I which is an I. Okay, once I fix that, I will look at this gi. Okay, namely g of f of m. Okay, that is from, again it takes this n, this gi into some a. Okay, so my map phi of mn, if I want to write it in a very notation, this is what it is. Yeah, right. Now you want to know that it's onto, is phi onto. This is well defined, there is no question now. Do you understand that? Is phi onto? Yes, because you start with any x in union ai. Okay, therefore there exists an I such that x belongs to a. It may belong to many I, but I don't care. But this I is some m of m, right? You follow that? Right. Now since x belongs to this ai, then this x must be some gi of n, because gi is a map of n onto ai. Therefore each x must be of the form gi of n. Okay, therefore if I take this m and n, okay, phi of m and n, then that is actually x. Okay, therefore it is onto. Okay, so what you have shown is countable union of countable sets. This is a very loose way of saying countable union of countable sets. Sets is countable. Okay, in particular, if a and b are countable, then a union b is countable, because I can write as a1 equal to a and a2 equal to b. Then my indexing set is 1 and 2, which is countable, and these are all countable. Therefore the result follows. Do you understand this? So this trick I could have used for a union b directly. Okay, right. So there are a lot more things which you will derive. Okay, but I think it's almost an hour, so I should stop it. Now do you see that you have some method of attack, you try to see, then you get stymied, then what do you do? That is the importance of equivalent characterization. Okay, which one works only with experience or by trial and error. I just wanted to show by trial and error. I wanted to use the first one condition, tried to do that, then I found the map was from A to Z plus cross Z plus, that's not even well defined. So what did I do? I changed the trick. Okay, I used the onto thing. You set your X is on countable if there exists an onto map from N on to X. That aspect I used. See, this is how one learns. See, many times teachers, they follow a book and they remember just because they prepare before the class and they explain. Okay, they don't even say what happens if I use other characterization. Can I get it? Okay, so those things make us understand better. So you should not think people already know it. No, it's by trial and error. Sometimes they know, sometimes they got on the onto thing, they were lucky, right? They stop. I hope all of you enjoy. We will continue. We will derive a lot of interesting things from these results about countable sets in the next lecture. Stay tuned. Take care. Stay safe.